Okay, so it's recording. Good. Now let me try to record the screen. Video, record, take video, and it is also recording. Good. So today we're going to start a topic called fluid dynamics. Actually, an introduction to fluid dynamics. Now, up until now, we've been treating fluids or studying fluids in statics, right? And when I say that I'm studying fluid statics, I'm simply looking at fluids that are at rest. So now, when I go to study fluid dynamics, I'm studying fluids that are, in motion. That's the difference between statics and dynamics. One is at rest, one is in motion. Statics was pretty easy because fluids are at rest. If fluids are at rest, then we know that our acceleration component is 0. If our acceleration component is 0, then pretty much anything related to the movement of the fluid can be neglected, including shear stresses. So we have defined fluids as substances that deform under shear stress. But now, if our shear stress is 0, then we don't really need to care about the deformation or movement of fluids. So if you look at fluid statics, we are essentially studying fluids from the perspective of a solid substance, a substance that doesn't really deform. Now, we're going to look at deformation. We're going to look at movement. We are going to look at the very core of what makes a fluid a fluid. So before we start studying this, I will give you a fair warning. The class is going to get significantly harder starting today. It's not going to be, oh, yeah, if I understood statics, I'm going to understand dynamics. They're two completely different classes, right? I mean, you have taken statics, I know. Has anybody taken dynamics or is taking dynamics? Okay, so you can tell that even though there's similar material, Newton's second law, it's not the same class, right? There's different things. You need to think about kinematics. You need to think about acceleration, right? You need to look at different types of coordinate systems. The same thing happens in fluids. We dealt with the static part of fluids. Now we're going to deal with the dynamic part of fluids. And in order to do so, we're going to have to learn a couple of ways to describe fluids. So the first thing I want to talk about today is the description of flows. In order to study fluids, we need to learn how to describe them. So let me write this down. So we're going to start with, description of flows. Could you close that door, Hannah? There are two different ways of looking at fluids. Now, first off, when I'm looking at a fluid, I need to first define what am I looking at. So in order to do that, I'm going to define a particle as a tiny, small element of fluid whose properties are pretty much constant. So when you hear the word particle, I know some of you may be inclined to think in terms of molecules or atoms. Don't think of it that way. A particle is essentially a small element of fluid, but it's still a continuous element. So we're not at the level where we're looking at individual atoms and molecules. We're still at the level where we're looking at what's identifiably a fluid, with density, with pressures, and with stresses, all that stuff. So if we define the smallest element of a fluid as a particle, then I can define my flow field as a group of particles that I am interested in studying. So I can look at my fluids as if they were collections of different particles. And that collection of particles is going to be my flow field or my region of interest. Now, in order to describe this flow, we need to consider two things. One, the fluid is moving. Now, because the fluid is moving, we can't think of things in terms of static time steps. We need to think of our fluid in terms of a moving time dimension. In other words, if I'm studying my fluids at a time t equals t naught, so maybe time equals 0, and then I look at my fluids at a later time, I cannot assume that my particles will be in the same place at a later time. Let me use a different pen. Okay? So if I look at my fluids at one time and I look at my fluids at a second time, my particles don't necessarily have to be in the same place because there will be motion in between the particles. Now, because there's motion in between the particles, there are two ways in which we will describe such motion. The first way is what we call the Lagrangian description. And the Lagrangian description, named after Mr. Lagrange, essentially focuses on the properties of individual particles. And by looking at individual particles, we can come up with relationships that are simply functions of time. For example, in the Lagrangian description, if we're looking at one specific particle, let's say the particle that I just shaded, I can say that the position of my particle is simply a function of time. I could say that the velocity of my particle is a function of time. I could say that the acceleration of my particle is a function of time. So in the Lagrangian description, we look at particles and their properties as functions of time. Now, there are some advantages to this approach. If we're looking at each individual particle and we're studying its properties, then we will essentially have properties for each individual particle in a flow, which means that our description of the flow, our model of the flow, will be probably more accurate. There are some disadvantages. If we consider a particle to be the smallest representable shape or volume of fluid to study, and we're trying to model flows in the Atlantic Ocean, how many particles do you think we need to study?
Over 7.
Yeah, more than 7. That's true. Maybe a little bit more, but right? So, yeah, you're not wrong, right? So, good job. The thing is that we're going to have to derive equations for each and every particle, right? And if we're studying a system with millions of particles, that means we're going to have to come up with millions of equations. Now, that doesn't seem like an efficient use of our time when we're modeling fluids. However, when we're studying systems where there are very, very small number of particles, think of the air around a spaceship as it re-enters the atmosphere. The molecules of air are actually so separate that the number of particles is pretty much countable, and we can actually come up with good equations that describe the flow of those particles. In that case, the Lagrangian approach is a good approach. But now when we're dealing with these... Yeah?
That might work during the entire re-entry, though.
Just during a certain portion where
the atmosphere is very thin.
That is correct. Once you're inside, it's not. It's just, again, millions of particles again. So if we cannot look at fluids from a Lagrangian perspective, then the next perspective I'd like to look at is called the Eulerian approach. The Eulerian approach was named after Mr. Euler. And if you took calculus, you probably heard that name before, Euler. You probably heard Lagrange before as well. But Euler, essentially, a genius in mathematics and fluids, he came up with an approach where instead of studying a particle, we study a finite control volume. And what happens? If we're studying a control volume, then really we only care about the particles that are inside that control volume at a specific time t. Which means that if the particles are inside at time t move outside of the control volume at time t plus dt, then we don't care about those particles anymore. So the Eulerian approach looks at a finite control volume where we only care about what's inside the control volume. We don't really care about what's outside the control volume. Now, through the Eulerian approach, we can apply the laws of conservation of mass, momentum, and energy, which I talked about very briefly in week number 2. And if we apply the laws of conservation to this control volume, then we can find relationships that express or that describe the motion of fluids inside the control volume with simply a small number of equations. For the most part, when we're studying fluids, at least from this analytical perspective, and we want to use the Eulerian approach, we're going to end up with 4 main equations. The 3 Navier-Stokes equations for flow, at least in the x, y, and z components, and the conservation of mass equation, all of which we're going to talk about later in the semester. But essentially, in the Eulerian approach, the properties of a fluid are actually going to be functions, let me start with velocity, are actually going to be functions of both position and time. So in the Eulerian approach, the position of a fluid, that is its x, y, and z location, is actually going to influence or help you determine the properties of the fluid at that point. So, two different approaches, Lagrangian and Eulerian. In this class, we're going to focus more on the Eulerian approach, but we are going to look to the Lagrangian approach whenever time permits. Okay? Now, when we're looking at fluids, it is important that we do a bit of a review of our vectors. So if you remember vectors, they are quantities that have magnitude and have direction. At least that's the simplest way of explaining what a vector is. So in this case, since our fluids are moving, our fluid properties, for the most part, not all, but for the most part, our fluid properties will have magnitudes and directions. Most of our transport properties will be vectors. Most of our thermodynamic properties will be scalars, but again, that is not always the case. So I'll give you an example of one of the most common vectors that you will study in fluid mechanics, and that is the velocity vector. In fluid mechanics, if we're studying a fluid in the x, y, z plane, then the velocity vector will have components in the x, y, and z directions. The component in the x direction is usually called u. The component in the y direction is usually called v. The component in the z direction is usually called w. Now, frankly, I know this may be a little bit confusing because you have a vector that you call v and then a y component that you call v. So we're going to have to do a bit of practice to get used to this notation. If you look at my notes, I try my best to keep my notes with a very consistent nomenclature. So you'll see that my velocity vector will always be in just regular font, and then my y component will always be in italics. I think I try to keep that consistent throughout my entire notes. Okay? No, we don't use specific volume in this in this class, thankfully. Thankfully, yeah. You will use it in thermodynamics, but thankfully you're not going to use it here. So now if my velocity has three components, an x component, a y component, and a z component, and I know that my x, y, and z positions are going to affect my velocity, then I can essentially calculate these three components. So if I want my x component of velocity, then I can simply calculate or find the x component by taking the change in my x direction with respect to time.
That'll become scalar, right?
Well, this is just the magnitude of this component, right? It's just a scalar magnitude of the component. Yep. Likewise, if I want my y component of velocity, then I just need to find the change in my y position with respect to y. And I don't think the third one needs any explanation, right? Our z component of velocity is simply the change in our z position with respect to time. So that is the velocity vector. That's the vector that we're going to use in this class extensively. Now we're going to find that there are different ways to describe not just the fluid or a particle of fluid or a volume with fluid, but we're also going to have to find ways to describe the path or the motion of a fluid. So we're going to define three types of lines that are going to help us identify fluids. The first such line is called the path line. And what is a path line? A path line is simply a line that's formed by the points that a particle travels through. For example, if I'm studying a small fluid particle, let's say that the fluid particle at time equals 0 is located at this position. Then at time equals 1, the particle is at this position. At time equals 2, the particle has moved, and so on. So we have 4 different snapshots at 4 different times of this fluid particle. And in each snapshot, the particle is in a different location. So then, how can we draw a path line? A path line simply covers every single point in space that the particle has traveled through over a finite amount of time. Now, what does this tell us? I can't say that I can draw a path line for time equals 0. Because at time equals 0, the particle is at one point. Rather, I would say that I can draw a path line from time equals 0 to time equals 3. So I need two ranges. I need a range of time in order to know how to draw the path line for my particle. A streak line is a line whose points are occupied by all particles that originated from a common point. For example, let's say we're looking at a water. You have the surface there. And let's say that you were to start dropping or pouring some sort of coloring or dye into the water. If I ask you to draw the streak line, I need to tell you the streak line that passes through which point. So I need to tell you which point the fluid passes to in order to draw the streak line. So in order to make this easy, if I want to say that I want my streak line that describes all the fluids that passed, or all the particles that passed through this point where the food coloring met the water, then essentially at time 0, this is my streak line, simply the fluids passing through the point. But at time equals 1, the fluids will have started to dissipate in the water. Perhaps at time equals 2, my streak line continues to grow because my fluids continue to move and more fluid continues to pass through my point of interest. Same thing with time equals 3, time equals 4, and time equals 5. So what does this tell us? The streak line essentially can be taken as a snapshot at one particular time. And as you move in time, your streak line will change. Because...
Tracking every single particle.
Sorry?
How is this different from tracking every single particle?
Because we're only identifying particles that pass through one point specifically. So when we're looking at a system as a whole, let's say we want to try to study mixing, right, from an oil spill in the Gulf of Mexico, right? Instead of trying to look at every single water particle, right, because we need to know the properties of the water to understand the properties of mixing with oil. Instead of doing that, what we're going to do is we're actually going to study the oil particles only. So even though in this system, oil is actually interacting with water, there is exchange of momentum and exchange energy between oil and water, we're actually only studying the oil, which is just one fluid in a system with two fluids. So it is a more simplified way of looking at a fluid. And finally, a streamline. And this will be the line that we're going to study most in this class. Now, a streamline and a path line may look similar at certain times, but they're not actually the same. You see, a streamline is a line that's tangent to the velocity vector at any point passing through it. In other words, if I were to take a snapshot at time equals 0, and at time equals 0, I want to know in which direction is this particle moving. And it happens that this particle is moving in this direction. So I'm going to look at the particle that is immediately next to it in that direction and say, in which direction is this particle moving? And if that particle is moving in this direction, then I continue to look at my particles. And what that's going to give me is essentially a line that looks like the path for a fluid particle, but may not always be the same. So how do streamline and path lines differ? Path lines require a finite set of time. You need a range of time. However, streamlines look at or can be taken in specific time snapshots. Path lines are lines for one individual particle moving. Streamlines are lines for multiple particles at one individual time step. Okay? So streamlines and path lines. In this class, we're going to study streamlines. And you'll see that it is possible for streamlines to change with time. However, if our flow is steady, which means if we don't have change with respect to time, our streamlines and our path lines will essentially look the same, even though one is for one fluid particle and one is for multiple fluid particles. Now we're going to have to turn to our math to find an equation for a streamline. So mathematically, we can find an equation for a streamline by studying vectors. Now if you remember, there was a vector that you learned in statics called the position vector. You remember what the position vector was? Can you say that again? Yeah, it's the r vector, right? And the position vector r essentially denoted the displacement from one point in space to another point in space. Now what this tells us is that as long as you had the coordinates of your points, then you had your position vector. And if you remember from statics, we said that calculating the position vector was as simple as taking the difference in your x, y, and z coordinates for that vector. Now, why do I care about this? If I were to look at a streamline and try to find a position vector for that streamline, you would notice one thing. If we're looking at a fluid particle, and I want the position vector from this fluid particle at time equals 0 to the same fluid particle at time equals 10 seconds, that particle may be far away. Let's say that at 10 seconds the particle has displaced to this point. My position vector essentially looks like this. However, from this position vector, because the time step is actually pretty big, 10 seconds, we can't assume that the particle is moving in a straight line from one place to the other. So let's say that I want to look at the position vector of the particle with a 5-second interval. And perhaps at 5 seconds, my particle has moved to this point right here. So my position vector will look like this. But once again, that position vector may not be descriptive of the motion of the particle. So try the first number that comes to mind. Which time step do you think would be small enough for our position vector to actually look similar to the streamline?
From the first to the second one we measured.
From the first to the second one we measured. And how are you sure that that can work for any streamline? Yeah, you're right. Sorry?
So we have to do the integral.
That's correct, right? Both of you are correct. You can look at a time step as small as whatever you have measured, but again, that does not tell you if your position vector actually accurately describes the motion of the path. So like Will said, we may have to turn to our friend Mr. Integral. Because if we really, really want a position vector that's small enough to describe the motion of a fluid accurately, and then you're on a curve, then really the only position vector that's going to describe that motion accurately is an infinitesimally small position vector, dr. And what are the dimensions of this position vector, dr? It's simply equal to an infinitesimally small change in the x direction plus an infinitesimally small change in the y direction plus an infinitesimally small change in the z direction. Now just to review, does everybody know what these I, j, and k vectors represent?
X, Y, Z.
Unit vectors in the x, y, and z direction. So these are simply unit vectors. Don't get too confused about them, okay? So now, if the position vector dr is small enough that it actually does travel along the direction of the streamline, and my velocity vector at a particular point in time does travel through that streamline, then I can find a relationship between the two by using a bit of vector operations. What is the cross product of two vectors that are parallel? Parallel. Zero, right? So now if my position vector is small enough that it actually describes the motion of the velocity correctly, then what I can say is that the cross product of these two vectors, my position vector and my velocity vector, is simply 0. And this is what we'll call the streamline equation, or the equation for a streamline. And actually, I'm going to call it the vector form of the equation.
Do they have a different form of the book?
Yep. So we have a vector form of a streamline, and we have two vectors that accurately describe flow, then we can use this equation to solve for the properties of a streamline. However, you'll see that sometimes it's easier to deal with scalars instead of vectors. So what I want to do today is I would like to use this vector form in order to find a simpler scalar form of the equation for a streamline. And the result of that scalar form will be what's essentially a differential equation. So let's go ahead and do that. Now, I'm not going to look at fluids in 3 dimensions today, because I would like for my analysis to be somewhat manageable and easy. So instead, I'm going to look for fluids in a 2-dimensional XY plane. So if I'm looking at a fluid in a 2-dimensional XY plane, my velocity vector is what? I have my x component, I have my y component. What would my z component be? 0, that's correct. Likewise, my position vector, my infinitesimally small position vector dr, will have an x component, a y component, and what would the z component be? Still 0, because we're looking at only 2 dimensions. So now, if I have a 2-dimensional flow field, and I want to find a scalar form of the equation for the streamline, then I'm going to start first with my vector form and see where that leads me. We know that the cross product of v and dr is simply equal to 0 because both vectors are parallel. But then if I want to solve this cross product, how do I do that? Yeah, you use the determinant matrix, right, to solve a cross product. Hopefully we're getting a good review in our vector operations, but if you don't remember, it's okay. The determinant matrix in a cross product is simply I, j, and k, so the directional unit vectors, the terms of the first vector, the terms of the second vector. So if I'm looking at the terms of the first vector, my velocity vector, what terms would I write? U, v, 0. What about for my position vector? That's correct. dx, dy, 0. And now I can solve this determinant in order to find the cross product. If you remember how to solve determinants, we typically start with the first unit vector times this minus this times this. And how much is that? Sorry? 0. Then we have our j vector times this minus this times this. How much is that? Sorry, this times this minus this times this. How much is that? Still 0. And finally, we're going to have our k vector. And if remember, our k vector will consider or will include these 4 terms. So we'll have our k vector times u dy minus v dx. And now to complete this equation, let's remember that the equation for a streamline was that the cross product of the velocity and the differentially small position vector is equal to 0. Now what this tells me is that my u dy minus v dx in the k direction is equal to what? 0. Okay. So now we're getting somewhere. Notice that k is never 0. K is a unit vector with a magnitude of 1. So which of these 2 terms have to be 0? It cannot be the k, so it has to be the scalar. Therefore, we get that u dy minus v dx is equal to 0. And I can rearrange this a little bit to say that u dy equals v dx. Now what I'm going to do is I would like to solve this as a differential equation. And perhaps the simplest way to solve this as a differential equation is to have my derivatives on one side and my functions on the other. And this is also the streamline equation. However, I'm going to call it the scalar form of the streamline equation. Now this scalar form, if you remember, has some limitations, right? It's a scalar form for a streamline in 2 dimensions. So if we're looking at a 3-dimensional flow, I cannot really turn to this scalar form. I would need to instead find a separate form of the equation by going back to my cross product. So I know the book pretty much jumps straight to the scalar form, but I need you to understand where the scalar form is coming from. Because when we're looking at fluids in 3 dimensions, we can't just write this equation. We need to also consider the z direction of the flow. Now, we've done a couple of derivations, been half an hour doing just definitions and derivations. So let's go ahead and try an example. This will be example 3.1 from your book. Now, in this example, we're going to have a 2-dimensional flow field. And if you're curious about how that flow field looks like, you can look at the figure in your book. But what I care about is the description of that flow field. This 2-dimensional flow field is described with the velocity vector 6yi plus 3j. And this velocity is in meters per second. Now let's do a quick review to see if we understand our vectors. What's the x component of the velocity? Six y, right? Because it is multiplied by the unit vector in the x direction. Therefore, that 6y describes the motion of the flow in the x direction. What's the y component of the velocity? Just 3. Now, what does this mean? It means that at any point in this 2D space, my fluid will always have a y velocity of 3. However, depending on my y position, my x component will vary. For example, and I'm just going to try to draw this in a Cartesian space. If my y is a negative value, in other words, if my fluid is in the negative y-axis, in which direction is my x component moving? Sorry? Exactly, right? If my y is on the negative side, then my x component is 6 times negative whatever my y is. That means that at anywhere below the x-axis, or at anywhere in the negative y space, my x component of my fluid particle will be towards the negative side. If my y is 0, so if my flow is on the x-axis, what's the x component of the velocity? 0, which means that at y equals 0, the flow is only moving in the y direction with a velocity of 3. And then if my y is positive, we know that the x component will be positive. So now if we were to find our vectors, all of my resultant vectors, I would see that the fluid described by this equation essentially flows in this way. Okay? So that's what that equation represents. That equation 6yi plus 3j simply represents a fluid that's flowing towards the left on the negative side of my y space and towards the right on the positive side of my y space. Now remember, this is an equation for a flow field. So this does not just describe a flow of one particle, it describes the flow of multiple particles in a field. Mm-hmm. Yeah. And we'll get there. So now the question is, what is the streamline equation for this flow? Now we can find the streamline equation without a problem, but I want specifically the streamline equation for the flow that passes through point 1, 2. In other words, if I define my point 1 meters, 2 meters, I want the streamline that passes through this point. I'm going to identify it in red. I want this streamline that passes through my point 1, 2. And when you see a problem like this, don't get too scared. We're just going to have to tackle it step by step. First off, we want the equation for a streamline. So let's try to find a general expression for a streamline without focusing on the location of your point 1, 2. So in order to find the general expression for a streamline, we turn to the streamline equation. Now, of course, we can write the vector form of the streamline equation, but how many dimensions does this flow field have? 2. So can we just skip to the scalar form that we just derived? Yeah. So let's go with the scalar form. dy over dx equals v over u. And let's see if we can solve this streamline equation. Okay? So we have dy over dx. Now that is simply a change, differential change in the y direction, differential change in the x direction. We have v, and remember when we're looking at our velocity vector, our components in the x, y, and z direction are called u, v, and w. So in this case, what's v?
What?
The y component, right? And what's the y component? 3. Good. Following that logic, what's u? 6y, that's correct. We can solve this a little bit. What's 3 over 6? That's 2, right? So I get 1 over 2y. And essentially what this leaves me with is a differential equation of the form dy over dx equals 1 over 2y. Now, has anybody here already taken diffie-q? Good. Is anybody taking it? Okay. Has anybody not taken it yet? Okay. For those of you that haven't taken it yet, today we're going to learn how to solve ordinary differential equations. In other words, today we're going to see how can we get this differential equation and find the value of y, or the equation that describes y. So what we have here is essentially an ordinary differential equation. An ordinary differential equation consists of a function and its derivative with respect to a variable. We call it an ordinary differential equation because the derivatives in this function are total derivatives. In other words, what we can say in this equation is that y is only a function of x. It's not a function of time, it's not a function of anything else, because this equation describes a flow field. So that my equation simply describes the path of the streamline of a particle. Okay? So looking at this equation, the question is, how do we solve it? Now, don't be scared. Just because it's an ordinary differential equation doesn't mean it's not solvable. In fact, you're going to find that it's actually a very easy to solve ODE. We're going to use a method, a differential equation method called separation of variables. Hannah, you said you took the class, right? Do you know what separation of variables is? Exactly. Separation of variables will require us to put all of our y's on one side, all of our x's on the other side. So that's what I'm going to do. I'm going to move all my y's to one side of the equation. I'm going to move all my x's to the other side of the equation. And look at this. We have an expression of 2y dy equals dx, where dy and dx are differentially small values. Now, somebody that hasn't taken the class before, I'm going to say you. You haven't taken it before, right?
I've taken it.
You haven't taken it before, right? Perfect. If you look at this expression, is there any mathematical operation that comes to mind that you think may help us solve it? We could take the derivative, but we don't know what y is. So if we can't take the derivative, what's the opposite of what we can take? Yeah, the integral, right? We have an expression with two differentially small elements. Therefore, we can integrate to find a solution for that expression. And what does this integral give me? I have the integral of 2y dy. What's the integral of 2y dy? That should be an easy one, right? Y squared, right? Because if you take the derivative of y squared, it's simply 2y dy. What's the integral of dx? And what am I missing here? A constant. Good. So this is a general expression for all the streamlines in this two-dimensional flow field. However, we want specifically the streamline that passes through point 1 meters, 2 meters. So if I have a general expression and I have a point that this curve passes through, how do I find the actual equation using this data? Exactly. We're going to plug in the coordinates of this point into this expression and find the value of c. In this case, I have that y equals 2. Therefore, I'm going to write my expression 2 to the power of 2 equals, and I have that x equals 1, so 1 plus c. Solving this for c gives us c equals 2 to the power of 2, that's 4, minus 1, that's 3. And finally, my equation for the streamline passing through the point becomes y squared equals x plus 3. And this is the streamline equation for this flow field that passes through this point. Okay? And that's how we find these equations. Now, I mentioned earlier that when we're studying fluids, we're essentially not trying to find numbers. We're going to try to find equations. And we're going to use those equations to then find our numbers of interest. Go ahead.
So it's a differential equation part that's separating the variable?
That's all it is.
Oh.
Yeah. I think in this class, when we get to differential analysis, we will start to look at more hard-to-solve differential equations. But for now, we're going to deal with ordinary differential equations that can all be solved by separation of variables. Okay? Now, this is not a calculus class. This is not a differential equations class. However, I will recommend that you learn some of the basic integrals, just so that when you see them, you don't spend too much time trying to find them, right? Especially when you're working on your homework. You want to spend your homework time trying to define and describe a fluid, not trying to find the integrals or the derivatives for a specific function, okay? So that's an example of the streamline equation. Now that we've done that, I'm going to spend probably what remains of the class going over some definitions. And I'm not a particular fan of just sitting down and reading definitions to all of you. However, these are terms that we're going to start using on our day-to-day in this class. So I think it's better that we at least have some exposure to these terms so that when it's time to define them, you have an idea of what I am expecting from them. So at the beginning of this class, we talked about how to describe our flows. Now we will talk about how to classify our flows. So, how do we classify our flows? There are different ways for us to classify our flows. And each classification really depends on what property of the flow we are interested in. So we're going to look first at classifying flows by their dimensions. Earlier, we just solved a problem where we had a velocity field in 2 dimensions in an xy plane. Such a problem is called a 2-dimensional flow problem. Now, why do we study 2-dimensional flow problems when obviously nature is very 3-dimensional? You see, sorry? We can get to a little philosophical argument about that, but that's not really the answer I'm looking for. I think you can. We can get into another philosophical argument about that, but there we go. Can you say that louder, please? Because it's easier. Can you imagine? Do you think our differential equation would have been that easy to solve if our flow was 3-dimensional? No, right? So why do we solve 2D problems? Because it is easier. So think of it this way. You are modeling. Well, I am modeling. I'll just give you an example from my own career. I am modeling the flow of a dam break in Cobb County. I actually modeled about 8 dams in Cobb County to develop what's called emergency action plans. What those plans tell you are these little maps that say, if this dam were to fail, these are the houses that are going to be impacted. These are the bridges that we need to close. And how do we do that? Well, we need to model that dam break. And that's what I did 4 years ago, I think. Anyway. Obviously, if a dam breaks, flow is going to move in 3 dimensions, right? The motion of my flow will be best described in 3 dimensions. However, if we're looking at a dam, specifically a dam in Cobb County, and we want to analyze fluid elements in that dam, we're going to have to come up with a number of really hard to solve equations. Now, if I want a software computer program to solve it for me, we're going to require a large amount of computational power and a large amount of time running those calculations. So instead, what do? I simplify my flow and look at it as two-dimensional. How do I look at my flow as two-dimensional? I say, well, there's a clear relationship between flow rate and depth, so I can just reduce my depth to just one variable that depends with the flow rate. And then the movement of the flow, I consider it to be only in 2 dimensions. Using that, we are able to develop these emergency action plan maps for Cobb County in a small, much smaller amount of time. Looking at it further, FEMA flood maps are these maps that tell you where the floodplain is. And when you're buying a house, one of the things that your lawyer asks you is your house on the floodplain, right? And what does that mean? That means that if a design storm, a 100-year design storm, which we'll talk about that much later, were to fall or were to impact your area, would your house flood or not? That's what those maps tell you. But how do you calculate those maps? You see, we have FEMA flood maps for the entire country. We cannot run 3-dimensional simulations for the entire country. We cannot even run 2-dimensional simulations for the entire country. So we simplify our flow as a 1-dimensional flow. We take all of our fluid properties that will determine our depth and our width of flow and look at them or simplify them to be variables of other fluid properties, such as depth and flow rate relationship, width, and the topography of the flow. And so all of our fluid properties then point in 1 dimension. So when we're looking at dimensions, we're looking at either 1-dimensional flows, 2-dimensional flows, or 3-dimensional flows. Now you got to be careful. I can't just say 1D is easier, therefore I will always calculate my fluids as 1-dimensional. I can't say that because sometimes a 1-dimensional approach will not be enough to model my fluid accurately. So instead, as an engineer, it's your job to look at a system and be able to determine what's the best and most efficient way of solving that system. And you'll find that sometimes it's easy or better or more efficient to model rivers in 1 dimension. Whenever I do my river models, I've done about close to 60 or 70 in Georgia. I've done more than 100 in other states. I'll mostly model them as 1-dimensional. Yes?
This is curiosity. So when you're modeling in 1D, like something like a river, is it essentially just like this is like a certain area and it's just like the extent?
Yeah, pretty much.
Okay.
And we're going to go into that a lot more detail when we study open channel flow. So don't worry. You're going to do a lot of modeling on your take-home exam. So it's okay. But anyway, I model most of my rivers as 1-dimensional. But when I look at things like dam breaks or maybe flows in very flat areas, I may model them as 2-dimensional. But when I'm looking at flows that probably have temperature gradients, pressure gradients, or some other wave gradient where I need to take into account motion in 3 dimensions, I may have no choice but to model my flows in 3 dimensions. So I can't just say I will model everything as 1-dimensional because it's easier and cheaper for me. Instead, I need to look at my system and make a decision based on what's best for the system. And that's why being an engineer is not just plugging and chugging numbers, right? It's making decisions as to what's the best way for you to make your calculations, what's the best way for you to analyze a system, and what's the best way for you to design a system. That's how we classify flows based on their dimensions. We can classify flows based on their viscosity. Now, we had already said in week number 2 that viscosity is a fluid's resistance to deformation from shear stress, simply a fluid's resistance to flow. However, sometimes our flows are so big that any friction from the boundaries of that flow can become negligible. Think, for example, of modeling flows in the ocean. Of course, we know that through oceanic currents, friction from the ocean bed is going to affect the overall flow. But how deep is the ocean? Deep. More than 7 feet. Thank you again, Will. So what we'll see if we're studying or modeling ocean currents, we'll notice that at a certain depth, the friction from the ocean bed stops becoming a factor in the overall flow. Now, when that happens, what we can do is we can simplify the flow above that level as simply inviscid or non-viscous flow. So we said that an inviscid flow is a flow where the effects of viscosity are neglected. Again, it can be any. Yeah. Oh, sorry. Yeah, this does not correspond to this. These are different ways of classifying, and they're independent of one another. Sometimes I cannot say that my flow is inviscid. If I'm looking at flow in a pipe, the friction between the pipe wall and the flow is actually going to affect the overall flow, which means that for those cases, my flow needs to be treated as viscous. Now, when we talk about fluids in real life, well, they're viscous, right? They're not inviscid. But the inviscid approach does help us come up with a couple of simplifications that will help our calculations. We can classify flows by regime. But our regime actually is only for viscous flows. You see, there are two main types of flow regimes. We call them laminar flows and turbulent flows. Now, laminar flows are pretty much self-explanatory. If you were to look at the flow as layers, then each layer essentially stays contained within itself. In other words, if you were to divide your flow into layers, fluid from one layer will not cross into the other layer. So flow pretty much moves in what's called a laminar motion.
If you recorded it, looks like it's unmoving.
If you were to record an external, so non-bounded laminar flow, it kind of looks like the flow is not moving. That's correct. If you see the video of the week for week number 2, you'll see a video where Destin from Smarter Every Day essentially kind of mixes two different colors of, yeah?
Yeah, it messed up. I've seen the other video before, though.
All right, I'll fix the link. But essentially...
It's the video on the cat and how it turns.
Oh, that's a good one.
Yeah.
That's also a good one.
You know.
Yeah, I'll fix the link then. But essentially, when I do fix the link, you'll see he essentially mixes two different food coloring dyes, but he maintains the flow regime laminar. And what does that mean? Since flow does not travel from one layer to another, when he brings the flow back, it essentially reverses the colors and the dyes return to their original colors. And that's what laminar flow is. It's flow that doesn't mix because it does not travel from one layer to the other, and therefore it is reversible. Turbulent flow is different. Turbulent flow does mix, and turbulent flow is unpredictable. Now, I don't mean unpredictable in the absolute sense that it's impossible to predict. I mean that given the tools that we have and the best of our knowledge and ability, we cannot predict it.
It's uncalculable.
Yep. Most turbulent flows, or most flows in nature, are turbulent flows. That doesn't mean that there aren't laminar flows in nature, because there are. But you'll see that most big flows are turbulent. So turbulent flows can include flows in pipes, but flows in pipes where either the pressure and temperature are high, all the way up to astrophysical flows in space. So flow of space dust, formation of nebulas, all of that is turbulent flows. The turbulent flows can be found anywhere, pretty much anywhere in nature. Now, whereas laminar flows are very interesting and beautiful to look at, turbulent flows are interesting because they are so hard to look at. They're so hard to predict. And when you're studying fluids, if you ever decide to work with fluids, you may end up having to make a decision whether you want to specify or specialize in laminar or turbulent flows. I think there are some other videos later on One is called Why Laminar Flow is Awesome, and one is called Turbulent Flow is More Awesome Than Laminar Flow. And they pretty much describe both types of flows. So you can look at those videos, assuming that I didn't mess up those links as well. Sorry? So the laminar flow is smarter every day. The turbulent flow is Veritasium, which they do videos together. Yeah, so Destin works with laminar flows. The other guy works with turbulent flows. So turbulent flows. Turbulence is an amazing concept. And it's amazing because it takes us not just to a scientific field, but it even brings us all the way back to a philosophical arguments, right? Can turbulence be predicted? Now, you know that from a scientific perspective, randomness is not a thing, right? What we perceive as randomness are simply patterns that we cannot recognize. But just because we cannot recognize them doesn't mean that they don't have a cause. So turbulent flow actually goes back all the way to the idea of chaos. And in physics, chaos is described, right, as a relationship where a small change in the initial conditions results in a big change in the final conditions. Now, you may have heard of the butterfly effect, right? The flap of the wings of a butterfly can end up causing a chain reaction that ends up with a tornado somewhere thousands of miles away. Now, I told this to my students last time. That doesn't mean that every time a butterfly flaps its wings, there will be a tornado. But what it does mean is that a change as small as the tiny pressure differential of a butterfly flapping its wings can eventually lead to very, very large, very, very catastrophic conditions in final conditions. So turbulent flow, the reason it's hard to predict, it's because it is chaotic. A very, very small change in initial conditions gives me a completely different change in final conditions. And the reason it is so chaotic for us from a mathematical perspective is that in order for us to model turbulent flow accurately, we need to consider every possible element that could influence that flow. So we're not just talking about pressures, stresses, and temperatures. We're talking about magnetic fields. We're talking about slight variations in the gravitational field that we're at. We're talking about electric fields. We're talking about any single thing that could slightly affect our flow. We need to take it into consideration. And sadly, we are at a point where we're looking to simplify our flows, right? Not make them more complex. So turbulent flow is an interesting monster altogether. I'd like to talk more about turbulent flow, but because this is an introductory class, we're going to treat turbulent flow from an engineering perspective. And from an engineering perspective, the answer to turbulent flow is, okay, let's not try to find an equation. Let's just see what it looks like in real life and then come up with some table or graph that describes it. Because that's essentially what engineering is, right? In engineering, we don't have time to try to describe turbulent flow with an equation when over the past hundreds of years, people haven't been able to. We need to instead use what we can observe to our advantage. So in this class, we will treat turbulent flow from an empirical or experimental approach. But if you are interested in turbulent flow, then we can talk more about that, okay? Another way of classifying flows, rather than flow regime, is through their compressibility. Can somebody remind me what compressibility was? Yeah, change in volume with respect to pressure, right? So compressibility is any change in volume or density with respect to pressure. Now we mentioned that we treat some fluids as incompressible, which means that we assume that their density doesn't change with respect to pressure, and then we treat other fluids as compressible. Now what does these two terms mean for us? If our fluid is compressible, then any change in pressure is actually going to deform my fluid, and therefore my properties such as density and viscosity will change. If my fluid is incompressible, then any change in pressure will not deform my fluid, and therefore I have less equations or parameters to worry about. Now, as an engineering approach, we can actually assume that most fluids are incompressible, liquids are incompressible. But we cannot do the same for gases. Because as you know, what's the definition of a gas when you're taking high school level or middle school level physics? We say that a solid retains its shape, a liquid takes the shape of its container, and what does a gas do?
It doesn't have that interaction with the other particles inside of it.
That's too advanced for middle school physics. It fills up the container, right? At least that's how I learned it, right? A gas fills up the container it's in. In other words, if I were to disperse a gas here, it's not going to stay here, it's not going to stay clumped, it's going to fill up the container. Sorry? Yes. But now, does the mass of my gas increase as it fills up my container? No. Only the volume increases. So if my mass doesn't change but my volume changes, that means that my density changes. So if the density of a gas changes constantly, we cannot treat it as incompressible. So you'll see for this class that our liquids will be treated as incompressible, our gases will be treated as compressible, and that's assuming that we actually get to a point where we can talk about compressible gases.
Then it is considered compressible.
Yeah. Yep. There are two more flow classifications that I'd like to talk to you about. And there are others in your notes, but I'm not going to go over them in this class. However, I'd recommend that you at least try to look at them. We can classify a flow as steady or unsteady. Now, what steady and unsteady mean is it relates the properties of my flow to its time derivative. Steady flow is a flow where the properties of the fluid do not change with time. In other words, if we could somehow simplify a fluid to a point where it has constant velocity, constant pressures, constant shear stresses throughout time, then we say that the flow is steady. Now this obviously is a simplification, but it is a simplification that allows us to calculate flows a lot faster. Steady flows are usually, not always, but usually modeled in industry as one-dimensional. Here we may look at steady flows that are two-dimensional or even three-dimensional because here we have math. We can do whatever we want with that math. But in industry, you'll see that most flows that are modeled as steady are for the most part one-dimensional.
Do they have to be linear?
They can be linear or measured through a streamline. So we'll talk about that in a second. So that's a good point. Now, unsteady flows are flows where the properties of the fluid change with respect to time. And those are the more realistic flows that we are used to. And finally, we can treat our flows as uniform or non-uniform. And what does that mean? You see, when we're looking at a flow, we can describe the flow geometrically through its streamline, right? And through a normal area to that streamline. That normal area to the streamline is called a cross-sectional area. For example, if I'm looking at flow in a pipe, and I want to take a cross-section of that pipe, what would that cross-sectional area look like? A circle. Yep, a circle. So when I say that my flow is uniform, I take or I assume that all my fluid properties in this cross-sectional area are constant. In other words, the velocity is the same here as it is here, as it is here, as it is anywhere in the cross-sectional area. So if I were to define my property as B, then the rate of change of B with respect to any dimension in that area would be simply 0. Okay? So that's what uniform means. Now, just as a discussion question, can I have a viscous and uniform flow? What do you think? Is it possible to have a flow that is both viscous and uniform?
Because that means that the velocity would be different throughout the area.
Exactly. If my flow were viscous, then the friction from the pipe would actually change my velocity. We'd have a lower velocity at the walls, a higher velocity at the center. And by that definition, uniform flow, or by the definition of uniform flow, our flow cannot be viscous, right? So even though these classifications are not mutually exclusive, you need to be careful. Yes, I can have a three-dimensional, viscous, turbulent, incompressible, unsteady flow, right? But no, I cannot have a viscous uniform flow, okay? So you need to kind of study these, or not study, but at least understand these classifications so that when you are simplifying your flow, you know which properties you can assume and which properties you can't. Now we have about 6 to 7 minutes left in class. And I'd like to use that time to talk a little bit about kinematics. Now, because we're only covering or talking about this topic one day this week, we're not going to be able to go over everything in class. So my recommendation to you is that you read the notes and just send me an email when you have any questions. Because there is a lot of math, particularly from this section onward, there's a lot of math involved. So now let's talk a bit about kinematics.
The velocity vector is typically presented in an XYZ plane. Now there's different ways of representing your vector. You can represent it in Cartesian coordinates, which is what we'll work on. You can represent it in cylindrical coordinates, spherical coordinates. But for now, I would like to start with what we're all familiar with, which is just Cartesian coordinates, right? X, Y, and Z plane. So if we're presenting our fluid in the XYZ plane, then the velocity essentially consists of an X component, which I'm going to call U, a Y component, which I'm going to call V, and this is a little bit confusing, but that's just what all fluid books call these components, and a Z component, which I'm going to call W. Now, before I move any further with this, do you understand what those I, J, and K vectors are? Okay, good. So those I, J, and K vectors are essentially unit vectors, right, that point in the X, Y, and Z axes, respectively. So if I call my U component, or my X component of the velocity U, that means that I can find U by taking the derivative of the X position of a particle with respect to time. Similarly, I can find V, and when I say V, I just mean the Y component of velocity, by taking the derivative of the Y component, or sorry, the Y position of velocity with respect to time. And finally, I can find my W by taking the derivative of the Z position of velocity with respect to time. So this is essentially my velocity vector with my X, my Y, and my Z coordinates. Now this is velocity. And we know from physics that acceleration is essentially the derivative of velocity with respect to time, something like that, right? So I can say, right, that my acceleration vector is simply the derivative of my velocity vector with respect to time. But then how do I quantify this derivative? I know that velocity is a combination of three components, but each component itself is a derivative of something with respect to time. So in order to figure out how we can quantify this acceleration, we first need to figure out what is velocity a function of. So the velocity of a fluid particle in most cases is going to vary with both location and with time, which means that we can take the velocity of a fluid particle to be a function of its Cartesian coordinates, x, y, and z, as well as a function of time. But when we're looking at a fluid particle moving in space, the location of that particle is also a function of time. Because if the velocity of the particle is a function of time, that means that the location of that particle is also a function of time, which means that my x-coordinate of the fluid will be a function of time. My y-coordinate of the fluid will be a function of time. And my z-coordinate of the fluid will be a function of time. And that's where things start to get a little bit complicated, because if I want the derivative of my velocity vector with respect to time, I need to consider that my velocity is a function of multiple variables, right? Not just time. And each one of these variables is itself a function of time. So then how can we quantify that derivative? We do so by using a rule from calculus called the chain rule. Now, I'm pretty sure all of you have learned what the chain rule is, but if you haven't, it's okay. We're going to review it a little bit. So the chain rule helps us find derivatives of functions that have multiple independent variables. In this case, that's exactly what we're looking at. We're looking at a function v that has multiple independent variables. But then these independent variables are themselves dependent variables of another independent variable. So it becomes complicated, but it's actually easy to grasp once we understand where everything is coming from. So let's figure out how we can apply the chain rule to this velocity vector. So the chain rule tells us that if I want to find the derivative of velocity with respect to time, then I first need to figure out what is the change in velocity with respect to each of these variables, and then multiply it by the change of each of these variables with respect to time. I'll explain myself. If I say that A, acceleration vector, is equal to dv over dt, so derivative of velocity with respect to time, then what I'm essentially saying is that to find the acceleration, I need to find the change in velocity with respect to time. That means that as time changes, velocity will change. But as time changes, position will change, and that position will also affect velocity. So let's look at this chain rule, one term at a time. If I want to find the change in velocity with respect to time, I first need to figure out how the velocity vector changes with respect to each and every variable. So I'll start with x, because it's my first variable right here. If I want to find the change in velocity with respect to x, I would simply write that acceleration is equal to the change in velocity with respect to x. But x itself is a function of time. So in addition to finding the change in velocity with respect to x, I now need to combine it with the change of x with respect to time. Now, does anybody know why this derivative has this squiggly term and this one is just a regular d?
Is it a partial derivative?
Partial derivative.
Thank you both. Yes, the squiggly little term is simply a partial derivative. In other words, if a function is a function of multiple variables, the partial derivative sets all other variables as constant and then simply takes a derivative based on only one variable. And obviously, the dx over dt, it's not a partial derivative because x is only a function of time. At least in our system, x is a function of time, so we don't need a partial derivative there. Good, but this is only the first term of our acceleration vector. We need to repeat the same procedure with my y, with my z, and with my t variables. So looking at my y variable, we say that acceleration will be equal to the change in velocity with respect to my y position, multiplied by the change of my y position with respect to time. We repeat the same thing for z. Change in velocity with respect to my z position, multiplied by the change in z with respect to time. And I'm still missing one more variable, right? I'm still missing my time variable. So once again, we get the change in velocity with respect to time, multiplied by the change of time with respect to time. And what we have here is what looks like an ugly equation, but once we learn how to use it, it will become beautiful in our eyes. Maybe not that much, but what essentially we have is a hard equation that's going to become easy once we learn how to use it. And even looking at this equation right now, we'll see that we can find ways to simplify it. Let's look at this most obvious simplification here. What's the change of time with respect to time? What's dt over dt?
1.
Yep. So this is just 1. And then if we look at these terms, we see that dx over dt is simply the u component of velocity. So dx over dt is just u. dy over dt is simply my y component of velocity, which is just v. And dz over dt is just w. So if we were to apply these simplifications to our equation, what we end up with is a more manageable form of the acceleration vector. So we see from here that the acceleration vector can be expressed as simply my x component of the velocity times dou v over dou x. So partial v over partial x, plus my y component of the velocity times partial v over partial y times plus my z component of the velocity times partial v over partial z. This partial is typically called dou. I'm still not used to that term to express a partial. And then I'm missing my time derivative, dou v over dou time, and this multiplied by dt over dt, which is just 1. And this is the acceleration vector, or at least it's the form of the acceleration vector that we will use in this class. It looks like a hard equation. If we look at how we would calculate acceleration back when we're looking at introductory physics, you might think, wait, it was supposed to be easier, right? Acceleration was just dv over dt, but this is dv over dt. But it's dv over dt considering velocity to be a three-dimensional vector that varies with position and time. So this is essentially your acceleration vector, and hopefully from this point onward, whenever you think of acceleration, you will think of this form of the equation. We have different types of terms here, and there are different names that we give these terms. This time rate term, that is the acceleration based on time, is typically called the local acceleration. And then the space-based acceleration, which depends on x, y, and z, is called the convective acceleration. Now what this means, why these names, right? Local acceleration is called like that because if we're following a particle, and wherever this particle goes, we follow it without caring where it is, just caring about the particle, then the acceleration of the particle, if we were to focus only on the particle and not on its position, is essentially partial v over partial t, and that's the local acceleration. We call this the convective acceleration because if we were to plot 1,000,000 particles, then this acceleration would essentially be represented regarding or based on its position. So because there's a change with position, we call it convective acceleration. So that is the acceleration vector, or at least that is how we will study the acceleration vector. I'm not going to expect you to memorize this vector, but I do hope that we get enough practice with the chain rule so that we can come up with this vector if we ever need to. So this is my acceleration vector. I'd like to talk about a couple of terms here. You see, when we're taking the acceleration, we said that we're taking the derivative of velocity with respect to time. But that derivative essentially gets expanded into 4 different terms. Now notice that each of these terms includes a vector, which means that each of these terms is actually 3 terms multiplied by I, j, and k respectively. So this is actually a very, very long equation. I'm just not going to write it all. But if you were to write this acceleration in terms of I, j, and k vectors, you would have all of this right, in terms of x with times I. Then all of this times j. Then all of this times k. So it's a very, very long equation, okay? Now, this derivative, the derivative of a particle or a property with respect to time, whatever property you choose, if your property depends on x, y, z, and t, it's going to look something like this, right? The only difference is that wherever you have your velocity vector, you're going to have whatever it is you're deriving with. And because this derivative is so important in fluid mechanics, we actually give it its own name. So we are going to call this special type of derivative the material derivative. So the material derivative is the derivative of a substance or the property of a substance when that property varies with space and time. Now, if you look at the material derivative, which we're going to just simply write as capital D over capital DT, then the material derivative is simply an operator that gives us the x component of the velocity of the substance times partial over partial x, plus the y component of the property times partial over partial y, plus the z component of the velocity of the substance times partial over partial z, times plus partial over partial t. I keep saying times when I should be saying plus. So I apologize for that confusion. I hope that you're actually looking at my notes because I say times, but I actually mean plus. So what does this mean for us? If we go back to the acceleration vector, we see that acceleration is the derivative of v with respect to time. So if we want to quantify acceleration in terms of the material derivative, essentially all we're doing is we're taking the material derivative of velocity with respect to time, which means that everywhere there's an operator, we introduce the velocity, and we end up with exactly the same equation we have here. So the material derivative is the derivative of a property of a substance with respect to time when that property varies with space and time. We call it the material derivative or sometimes the substantial derivative because it follows the substance, right? It follows the substance or the particle through space and through time. So this, at least the green part, is the material derivative. Now, you'll notice that in order to study these fluids, we have different sets of coordinate systems. We have what's called the Cartesian coordinates, which is an x, y, z space, which I think most of us, if not all of us, are already used to. However, there are other types of coordinate systems that we are going to use in this class. For example, we can also look at fluids in terms of streamline coordinates. And what do I mean when I say streamline coordinates? You see, a fluid, or a fluid particle to be exact, typically travels through its streamline. In other words, if I were to draw a streamline, that is a line that is tangent to the velocity vector, it is expected for my fluid particle to travel along the streamline. So if I'm studying a tiny fluid particle, that tiny fluid particle is going to travel along this line. Now this streamline actually makes some of our calculations a little bit easier if we can define the streamline. So if we know the streamline where the fluid is, or the fluid particle is traveling through, then we can say, instead of looking at our coordinates in terms of an x, y, z space, we can look at our coordinates in terms of a streamwise direction. In other words, the direction of the fluid particle along the streamline. So I'm going to call this axis, the streamline axis, my S axis. Now in streamline coordinates, we still need 3 dimensions. Well, we can't just have one s-axis and call it a day, because there is curvature in the streamline. So whenever there is a curvature, we are going to call the normal direction, that is the axis perpendicular to the streamline that points towards the center of curvature, the normal axis or n-axis. Now the normal axis is always perpendicular to the streamline. Just like our x, y, and z axes, right? They're all perpendicular to each other. The normal axis is always perpendicular to the streamline. What makes the normal axis different is that its position, its positive direction, depends on where the center of curvature is. So at this point in the particle, my normal axis is pointing towards the top of the paper. But at this point, where the center of curvature is at the bottom, my normal axis will be pointing towards the bottom of the paper. So this normal axis actually varies depending on where in the streamline you are, because it always points towards the center of curvature. The final axis is simply an axis that's perpendicular to both, right? And just like we have an x, y, and z axis, we can have an s, an n, and a y axis that will be normal to the paper, so pointing outside of this paper, pointing towards you. So I'm not going to draw it here to avoid confusion, but the y axis, which will be my third axis, is just an axis perpendicular to both. Now we'll see why streamlines make our work a little bit easier. If we're looking at streamline coordinates, the first thing that we can see is that the velocity vector will always be tangent to the streamline. In other words, the velocity vector will always be along the direction of the streamline. Now what that means is that if I could define a unit vector, a tiny, tiny, tiny unit vector with magnitude 1, actually not that tiny, with the magnitude 1, then the velocity vector is equal to the magnitude of the velocity times my unit vector. If you don't remember this, I have some statics lectures where I explain this, not in fluids terms, in terms of force, but any vector is equal to its magnitude multiplied by a unit vector in its direction. That's one of the definitions of vectors, right? Now, if the velocity vector is tangent to the streamline, we can define the velocity vector as simply the magnitude of the velocity times a unit vector along the streamline. That's one thing. The second thing we need to see is that the streamline is always in the direction of the velocity vector, which means that at any point in my streamline, my velocity vector only moves along the direction of the streamline. That means that there is no velocity in the n direction. There is no velocity in the y direction. The only velocity is the velocity along the streamline. So this magnitude of the velocity vector is simply equal to whatever the streamline component of velocity is, because my normal velocity and my y velocity are both 0. So that's another simplification of streamline coordinates. Finally, when we are calculating the acceleration of a streamline, we're not going to go through the whole derivation, but if I wanted to calculate the acceleration of a streamline, I can simply calculate it by taking the material derivative of velocity, which in this case, velocity will be a function of its position along the streamline following the s and y axes. So what does this give me? If we look at the acceleration in Cartesian coordinates, the acceleration in streamline coordinates will actually be very similar. Instead of the velocity component in the x direction, we'll have the velocity component in the s direction, in the streamline direction, multiplied by the partial change in velocity with respect to not x, but a streamwise direction. So partial v over partial s. Likewise, instead of having the velocity component in the y direction, we'll have the velocity component in the normal direction, multiplied by partial v, partial n. We do the same thing for what would be RC, which is just my velocity component in the y direction, multiplied by partial v, partial y. And finally, we have our time derivative. But now, if you look at this equation, and we look at the simplifications that we just made, we can actually simplify this equation a little bit further. You see, we said that Vn and Vy is 0. Why? Because my velocity only moves along my streamline, which means that there is no velocity in the normal direction. There is no velocity in the y direction. So if Vn is 0 and Vy is 0, then my velocity vector, my acceleration vector actually becomes much more manageable. Because essentially, all we have is that the acceleration is equal to my streamwise component plus my time components. And we can simplify this even further. Because now, when we look at our acceleration vector, we see that there is really no velocity component in the y direction. There is no velocity component in the n direction. So I can break down my acceleration vector into the s, n, and y components as follows. So the s component is simply Vs times partial of the velocity in the streamline direction with respect to s, plus my partial derivative of velocity in the streamwise direction with respect to t. I can repeat the same process for an and ay, but I'm not going to do this here. So why do we do all this, right? We can do all this because looking at our fluid in streamline coordinates is going to simplify, right, our calculations. We take what's essentially a 4 times 3, a 12-term equation, and we simplify it into a 2-term equation. Now, of course, in order to use this streamline coordinate vector, we're going to have to learn a little bit about how flows travel through streamlines, and that's all we're going to do during the next couple of weeks. So I wouldn't want you to focus too much on this. I would recommend that you read the notes so that you can see how we derive the acceleration vector in the n direction. But other than that, are there any questions with this material so far? I know it was pretty abstract, right? It was pretty mathematical, but any underlying questions right now with the math or with the content?
For the streamline, you said that velocity only follows directly in line with the stream, correct?
That's correct.
Okay, thank you.
Yeah, the velocity is always, because the definition of a streamline is a line that's always tangent to the velocity vector.
Okay, gotcha. Thank you.
Yep. So there are no more questions. I would just recommend that you review your calculus a little bit if you need to, but if not, then it's okay. We're going to do a lot of calculus here.